You are also expected to analyze LeChatelier's principle based on graphs. You'll see a number of these examples in your textbook, typically broken off into smaller sections of individual stresses. Essentially what we have here is a graph of the concentration of our reactants and our products versus time. Okay, so I'll just put in a random time schedule here. Okay, so first thing that you might be asked is at time 2, what's happened? Well, at time 2, we see that all of the concentrations have leveled out. So chances are what has happened at this point is we have now reached equilibrium. Okay, all the concentrations have stopped changing, therefore the reaction has been finalized. Now, if you saw flat lines later on in a graph, you could also say maybe a catalyst has been added. Okay, again, that's only if you see this further down the graph. Okay, all right, let's look at another one. So as it says here, all 3 lines leveled out and has been reached. When we see a large spike, like we're seeing right here, that only means one thing. When you see the big spike, it means you've changed the concentration. Okay? In this case, we see that the concentration of ammonia has decreased. Well, to confirm that, say, okay, well, I think the concentration is decreased, so then I can look at my shifting. Well, if I decrease the concentration of ammonia, I should shift like this, which means the response of the graph should be that ammonia should go back up, which it has. You can see that down here. And the concentration of nitrogen and hydrogen should decrease, which you see here and you see here. And so that would be an accurate depiction. So one single sharp spike equals a concentration change. If I see multiple spikes, as in this example, notice they're smaller than the other one. Multiple spikes means everything's changing concentration. They'll always be in the same direction. We're going down, we're going down, we're going down again. Well, when we have these multiple spikes, that means that we have altered the pressure or volume. Okay, so then I have to figure out what I've done. So if I've decreased the concentrations of everything, that must mean I've increased the volume of the system. And if I've increased the volume, that means I'm going to shift to the side with more moles. So I must have increased the volume in this example. Volume has gone up, which means I'm going to shift to the side with more moles. Which in this case is the reactants. Again, I could verify that. If I think I should have shifted the reactants, that means I should have more N2 and H2, which I do. They've both gone back up, and the ammonia has gone down. Now for this example, you'll notice there aren't any sharp spikes. They're all 3 are kind of gentle curves, either increases or decreases. When that happens, that means I've had a change in temperature. Okay, so then to figure out whether it's gone up or down, let's look at the shift again. Well, my reactants have both decreased, my product has gone up, which means I must have shifted like that. Well, if I've shifted like that, that means I must have shifted to the right, shifted the products. So what does that mean I had to do the energy? Well, the energy is a product, which means I must have taken away energy, which is a decrease in temperature. Right? Decrease in temperature of the system. And that's how you analyze graphically.